So here we are looking at the 6 standard quadratic surfaces. And while the family of quadratic surfaces is quite large, we're going to focus on these basic 6, and we'll be able to use them to derive different adaptations of the quadratic surfaces. So I want you to note as we get started that A, B, and C are going to be our scalars. These are constants or real numbers. And for each one of these quadratic surfaces, I'm going to center them at the origin, but keep in mind that they can be centered at any arbitrary point. So our first surface is the ellipsoid, and it is defined as x squared by a squared plus y squared by b squared plus z squared by c squared is equal to 1. And now an important feature of the ellipsoid that I want to point out is that all of the coordinate traces are ellipses. So all coordinate traces are ellipses. So looking at the graphical representation of the surface of an ellipsoid, we can see these different traces. We have, here is our xy trace. So remember, the xy trace is where z is equal to 0. We can see the xz trace here coming down from above. So your xz trace is when y is equal to 0. And last but not least, we can see our yz trace going around our ellipsoid. So this is our yz trace, and that's when x is equal to 0. So each one of these two-dimensional traces, these coordinate traces, helps us in sketching our ellipsoid in 3 dimensions. Our next quadratic surface is the hyperboloid of one sheet, and this is defined as x squared by a squared plus y squared by b squared minus z squared by c squared, and this is equal to 1. So with the remaining surfaces, it's important to note that I'm just giving you one possible way to write this surface. So if you notice here, the coefficient of z has a negative coefficient, but we could switch that negative to x and y as well. So when you're thinking about the features of your hyperboloid of one sheet, you want to keep in mind that this surface is centered about the axis, whose variable has a negative coefficient. So the surface is centered about the axis, whose variable has a negative coefficient. So for this notation, or for this example, here it's centered about the z-axis, because z has the negative coefficient. I also want you to note that for all real numbers z0, the traces with z being equal to that constant z0 are ellipses. So we say for all real numbers z0, traces defined as z is equal to z0 are ellipses. And this is going to include the xy trace. And now additionally, for all real numbers x0, y0, traces with x is equal to x0 and y is equal to y0 are hyperbolas. So looking down at our graphical representation of this surface, we can see these different traces. We can see here is the xy trace. So the xy trace is when z is equal to 0. And we can also incorporate traces for other values of z to help us establish that three-dimensional surface. We can also see the hyperbolas for both the yz trace and the xz trace. So here are the yz traces. So this is when x is equal to 0. And we can also see the hyperbola for the xz trace. And the xz trace is when y is equal to 0. The next quadratic surface we are considering is the hyperboloid of two sheets. So one way to define this is using the equation minus x squared by a squared minus y squared by b squared plus z squared by c squared is equal to 1. And looking at this given equation here, we notice that the coefficient of the variable z has a different sign than the others. So this is indicating to us that the surface is centered about the axis whose variable has a coefficient of a different sign, or in this case, has a coefficient that is positive. So the surface is centered about the axis whose variable has a positive coefficient, or a coefficient of a different sign than the other variables. So in this case, we can see that our surface is centered about the z-axis. So while we're talking about z, let's think about some of the z traces. So I want you to note that traces with z being equal to some real number z0, so this is such that z0 is an element of the real numbers, with the absolute value of z0 being greater than c. So keep in mind here from algebra, we know that this inequality, this absolute value inequality, is equivalent to saying that z0 is going to be less than negative c, or that z0 can be greater than positive c. So traces with z being equal to z0 of these conditions are ellipses. Now, similarly, traces with z being equal to some z0, such that z0 is a real number, but here we have with the absolute value of z0 being less than c. So again, keep in mind from algebra that this is equivalent to saying that z0 is greater than negative c, less than positive c. These traces do not exist, so there are no traces. And you can see that by looking down at your graph here, these vertices of our surface are occurring at positive c and negative c. And notice that for any z value in between those two values, there's no surface. So those surfaces do not, or those traces, do not exist. And we'll make one little love note as we've indicated below that vertices or singleton points exist at plus or minus c. So the coefficient of the variable associated with the axis of symmetry. So we have vertices or singleton points at 0, 0, positive c, and 0, 0, negative c. So lots of good stuff going on with this surface. So this is just for traces associated with z values, but what about x's and y's? So I want you to note, last but not least, that traces with x being equal to x0 or y being equal to y0, such that x0 and y0 are real numbers, are hyperbolas. All right, so these are some of the important features to keep in mind for your hyperboloid of two sheets. So we've already indicated these singleton points on our graph, and we can see that as we let z naught vary to a value greater than positive c, that our traces are ellipses. The same thing occurs if we let z naught vary to a real number below negative c. We can see we have an ellipse. Now we can also see the hyperbolas created by the x and y values. So looking at a yz trace, we can see the hyperbolas. So here's a yz trace, which we of course recall is when x is equal to 0, and this occurs both above and below the xy plane. And we can also see the hyperbolas associated with the xz trace. And again, we recall that in xz traces where y is equal to 0. The next quadratic surface on our list of basic surfaces is an elliptic cone. So one way to define an elliptic cone is by x squared by a squared plus y squared by b squared minus z squared by c squared, and this is equal to 0. Now again, looking at this equation, we notice that the variable z has a coefficient of a different sign than the others. So this indicates to us one of the important features of an elliptic cone, and this is letting us know that the surface will be centered about the axis whose variable has a coefficient of a different sign. So we can say that the surface is centered about the axis whose variable has a coefficient of a different sign. And we can even, we'll simplify this, who has a negative coefficient. So again, looking at our surface here, we can see that this variable, the axis of symmetry, is going to be about the z-axis. Now, while we're talking about z's, let's think about some of the z traces. So we can say that traces with z being equal to z naught, such that z naught is a real number, so a scalar value, with z naught not being equal to 0. So traces of this nature are ellipses. Now we also want to note here that when z naught is equal to 0, so when z naught is equal to 0, we're going to have a singleton point at the origin. So a vertex or a singleton point at the origin, 0, 0, 0. And we can see that in our graph below. We have that singleton point there right at the origin. Now, in addition to this, we want to think about what about the traces for x and y values? So we say that traces with x being equal to x naught and or y being equal to y naught, such that these x naught and y naughts are real numbers or scalars. So these traces are either going to be hyperbolas, or we have intersecting lines. And these intersecting lines are the coordinate traces. So this is when x is equal to 0 and when y is equal to 0. So for all other values of x and y, we'll have hyperbolas as the trace. So let's think about these traces on our graph. So again, we've already indicated that singleton point here at the origin, and then if we let z vary to a value greater than 0, we can see the trace is an ellipse. Same thing if we let z be a real number below 0, we have a trace of an ellipse. And now we want to think about the coordinate traces in the YZ plane. and the xz plane. So for the yz plane, here are the intersecting lines. So these are the yz traces. And of course, we will call it a yz traces when x is 0. And last but not least, we have the coordinate traces for the xz plane. And so these are, again, intersecting lines. These are the xz trace, those intersecting lines defined when y is equal to 0. The next quadratic surface we are looking at is the elliptic paraboloid. And one way to define an elliptic paraboloid is as z by c is equal to x squared by a squared plus y squared by b squared. So notice here that the z variable is the only variable in this equation of degree 1. So this is indicating to us that the surface is centered about the axis whose variable is of degree 1. So our first important feature, the surface is centered about the axis whose variable is of degree 1. Now, once you have identified the variable of degree 1, and you know the axis of symmetry, we want to go ahead and determine how is this paraboloid opening? Is it opening towards the positive axis or is it opening towards the negative axis? And we use similar knowledge to that from R2. So we can say that if the coefficient associated with this variable is positive, then the paraboloid opens towards the positive axis. So we can say that if the coefficient is greater than 0, and again, this is the coefficient associated with the axis of symmetry. If the coefficient is greater than 0, it opens towards the positive axis, versus if the coefficient associated with the axis of symmetry, if this coefficient is negative or less than 0, this means that the paraboloid opens towards the negative axis. Now, while we're talking about this z, let's think about some of the z traces. So we can say that traces with z being equal to z naught, and this of course is such that z naught is a real number with z naught being strictly greater than 0, these traces are ellipses. And a couple of little additional love notes here. We have that if z naught is equal to 0, we have a vertex or singleton point at the origin. And then last but not least, if we have a z naught that is less than 0, in this case, it's not going to exist. So there are no traces. This does not exist. And again, these traces will change depending upon how your paraboloid is opening. So here in our case, we are assuming that our coefficient is greater than 0. So our paraboloid is opening towards the positive z-axis here. So for z naughts less than 0, for real numbers of z less than 0, there are no traces. Now, last but not least, what about the x and y values? What about these traces? So we say that traces with x being equal to x naught and or y being equal to y naught, such that x naught and y naught are real numbers, these are parabolas. So let's go ahead here and think about these traces on our graph. So we can see we have this singleton point or this vertex at the origin. And then if we let z be a real number greater than 0, we see we have a trace of an ellipse. And then thinking about the coordinate traces in the xz plane and the yz plane, we can say here is the yz trace. So we'll keep in mind, of course, that the yz trace is when x is equal to 0. And last but not least, we have the xz trace. So again, we have that parabola for our xz trace. Then the xz trace is when y is equal to 0. And the last quadratic surface that we need to explore is the hyperbolic paraboloid, which is also sometimes called a saddle. So one way to describe a hyperbolic paraboloid is by z is equal to y squared over b squared minus x squared over a squared. Now, looking at this equation, we again notice that here our z variable is of degree 1. So we say that the surface is centered about the axis whose variable is of degree 1. So our surface is centered about the axis whose variable is of degree 1. So again, for this example, or for this way to define the hyperbolic paraboloid, here our surface will be centered about the z-axis. But as always, with all of these quadratic surfaces, it can vary between x, y, or z. It's all how we define it, or how it's given to us. Now, with z in mind, let's think about the z traces. So we say that traces with z being equal to a z-naught, such that z-naught is a real number and z-naught cannot be equal to 0. So these traces are hyperbolas. Now, what about the traces for x and y? So we say that traces with x being equal to x-naught and or y being equal to y-naught, such that x-naught and y-naught are real numbers. These traces are parabolas. And we can easily see our parabolas in our graph below. So if we're thinking about the coordinate trace defined by the xz trace, see here is our xz trace, or that parabola defined by our xz trace. And of course, the xz trace is when y is equal to 0. And now we can also see copies of this parabola on either side. So these are traces parallel to the xz plane. And we can also see the coordinate trace in the yz plane. So here is that concave up parabola. This is our yz trace, which we know is, of course, when x is equal to 0. And now one final fun love note here is what's going on at the origin. So we have this singleton point here at the origin, 0, 0, 0. Now I want you to think about a small open region around this point. Notice if you're thinking about the parabola in the defined by the xz trace, that this singleton point is a maximum point. Versus if you're thinking about a small open region around this ordered triplet, and you're thinking about the parabola defined by the yz trace, notice that it's a minimum point. So this is a fun feature that we're going to look at when we explore curve sketching and extrema with surfaces, that not only do we have maximum points and minimum points, but we also have points that are both. Those are called saddle points. So get excited. We'll be looking at this in more detail at the end of this chapter.